Hello everyone. This video is about Chapter 3, Probability. Probability plays an important role in making inferences. Probability is everywhere, such as the weather report, sunny or raining, the chance to win a gambling game. Let's begin probability with a straightforward example of tossing a coin that is easily described. Suppose a coin is tossed once and the up face is recorded, a head or a tail. Toss a coin and observe whether it results in a head or a tail. We call it an experiment. Because observing the outcome of an experiment is similar to selecting a sample from a population, the basic possible outcomes of an experiment are called sample points. For example, observing a head is a sample point, and observing a tail is also a sample point. The sample space of an experiment is the collection of all its sample points. Let P represent the probability of sample point. As we know, there is an equal chance of a head or a tail. So the probability of a head or a tail is half, 1/2. The probabilities must obey two rules. Let Pi represent the probability of sample point I, then 1. All sample point probabilities must lay between 0 and 1. 1 is 100%. For example, we will not say that there is a minus 20% of chance of raining tomorrow or 300% chance of sunny tomorrow. 2. The probabilities of all the sample points within a sample space must sum to 1. For example, the probabilities that you pass the exam and you do not pass the exam sum to 100%. A useful tool is a tree diagram. Two coins are tossed and their up faces are recorded. List all the sample points for this experiment by a tree diagram. You can draw the tree diagram from the top to the bottom or from the left to the right. At the top of the tree, there are two branches representing the two outcomes, H, head, or T, tail, for the first tossed coin. Each of these outcomes result in two more branches, representing the two outcomes, H or T, for the second tossed coin. Consequently, after tossing both coins, you can see that we have 4 sample points, HH, HT, TH, TT, where H in the first position means head on coin 1. H in the second position means head on coin 2, and so on. Another definition is an event. An event is a specific collection of sample points. The probability of an event A is calculated by summing the probabilities of the sample point in the sample space for A. We will use the example of tossing two coins again to explain. If you consider the event A, observe exactly one head. Then event A contains the sample points HT and TH. If you consider event B, observe at least one head. Event B contains the sample points HH, HT, and TH. Another method of determining the number of sample points for an experiment is to use computational mathematics. Suppose a sample of small n element is to be drawn without replacement from a set of big N elements. Then the number of different samples possible is calculated as follows. This is called computational rule. Here is an example. Suppose a movie reviewer for a newspaper reviews 5 movies each month. This month, the reviewer has 20 new movies from which to make the selection. How many different samples of 5 movies can be selected from the 20? For this example, big N is 20 and small n is 5. Then the number of different samples of 5 that can be selected from the 20 movies is 15,504. Note that 20 factorial equals 20 times 19 times 18 times 17 up to times 1. An event can often be viewed as a composition of 2 or more other events. Now, I'll introduce 2 definitions, unions and intersections. What's the difference between them? The union of 2 events, A and B, is the event that occurs if either A or B, or both, occurs on a single performance of the experiment. The intersection of 2 events A and B is the event that occurs if both A and B occurs on a single performance of the experiment. So, a union is useful for working with A or B, where the intersection is useful for working with A and B only. Another useful concept is complementary. The complement of an event A is the event that A does not occur. That is, the event consisting of all sample points that are not in event A. We denote the complement of A by AC. For example, if A is passing the exam, then the complement of A is not passing the exam. The sum of probability of A and AC equals 1. That is, if the chance of passing exam is 90%, the complement not passing the exam is 10%. You can see that the probability of the union of 2 events A and B can be obtained by summing probability of A and probability of B and subjecting the overlap, because the overlap A and B have been included twice. So the formula is probability of A or B, the union, equals the probability of A plus the probability of B, and then subject the overlap A and B. We call this formula additive rule of probability. Event A and B are mutually exclusive if A and B have no overlap. For mutually exclusive event, the probability of the overlap will be 0. So, if they are mutually exclusive, the probability of A or B equals probability of A plus probability of B. Often, we have additional knowledge that might affect the outcome of an experiment, so we may need to alter the probability of an event of interest. A probability that reflects such additional knowledge is called the conditional probability of the event. To find the conditional probability that event A occurs given that event B occurs, divide the probability that both A and B occur by the probability that B occurs. Be very careful here. B here is the given condition. Here is an example of a two-way table, which is also called contingency table. If a customer complaint is received, what is the probability that the cause of the complaint was the appearance of the product, given that the complaint occurs during the guarantee period? Let A represent the event that the cause of a particular complaint is the appearance of the product, and let B represent the event that the complaint occurred during the guarantee period. We can calculate the conditional probability that the cause of a complaint is appearance, given that the complaint occurred during the guaranteed time, as follows. Probability of A and B divided by probability of B equals 0.51. Based on the conditional probability formula, we can develop another formula, which is often called the multiplicative rule of probability. That is, the probability of A and B is unknown. You can derive from the conditional probability and the probability of A or the probability of B. Event A and B are independent events if the occurrence of B does not alter the probability that A has occurred. That is, even given a condition, the probability is still the same. Let's go back to the example to check whether event A and B are independent. As we calculated before, the conditional probability given B is 0.51. Only if probability of A given B equals to the probability of A, they are independent. However, the probability of A, the cause of the complaint is the appearance of the product, is 0.32 plus 0.03 and equals 0.35. They are not equal to each other. Therefore, A and B are dependent. That's all for this video.